So today we're going to be talking about vision, which is probably one of the more complicated parts of programming in FRC because it's got a pretty steep learning curve, but once you know what you're doing, it becomes a lot easier as long as you make use of all the resources that are at your disposal. So, um, in almost every single FRC game, first provides us with some sort of challenge that we need to target. And in order for us to aid in finding these targets, they outline the target in some kind of retroreflective tape that looks a little like this. And retroreflective tape interacts with light waves differently than most reflective surfaces. So instead of reflecting light at the same angle that it hits a surface at, it bounces back directly back to the origin from which it came from. So, how do we take advantage of this retroreflection in order to find and isolate our targets? We can position a camera right inside a bright ring light, which is typically just an array of LEDs, and this light will shine so brightly directly at the retroreflective tape that the light will bounce right back into the camera and it'll show up as a very bright spot in the camera feed. And typically we'll use some kind of bright and unusual color like green because it makes isolating green spots in an image much easier for the software later down the line. And in terms of software, there are many routes that you can choose when trying to perform image processing. And each of these have their own pros and cons, but the end result should be software capable of isolating a vision target from the rest of the image. And this is done through a process called computer vision, which is an overarching subject that tries to teach a computer how to interpret the visual world. And no matter what option you choose to go ahead with, almost every single implementation uses this library known as OpenCV. And OpenCV is a computer vision library that has main implementations in Java, C++, and Python, which coincidentally are the three most used languages in FRC. And it's such an extremely powerful library that you can do almost any computer vision application imaginable. So say you want to build a vision algorithm from scratch, you could build some sort of pipeline using an OpenCV implementation and run it on some coprocessor on your robot. And a coprocessor is simply an additional computer that you place on the robot right alongside the RoboRio. The RoboRio, as you guys know, is the main brains of the robot. It runs all the robot code and it's responsible for transforming any inputs that the driver station gives to the actual motors and the mechanisms running on the robot. So we place a coprocessor alongside the RoboRio to handle the intensive calculations and operations that we sometimes have to do. Since computer vision takes a decent amount of resources, we typically don't want to task the RoboRio with running the robot code and the vision at the same time, because then you'll start to experience some latency. The robot code loop will start to slow down, and you'll get some latency between the driver station and the actual robot, which will result in some lag and some unwanted effects. So we typically offload this work onto a coprocessor like a Raspberry Pi, or some teams have started using NVIDIA Jetsons, which are essentially small computers that are dedicated for computer vision applications. Now, by writing your own pipeline in OpenCV, you have full absolute control over whatever image processing that you want to do. But it has some downsides because it requires a fair bit of knowledge of the actual OpenCV library. It requires time, lots of tweaking, and it's far out of the scope of today's workshop. Now, another option that is a bit more appealing would be using this tool written by WPI called Grip. And Grip is a graphically represented implementation of OpenCV with some extra features sprinkled on top. What you can do is you can essentially drag and drop and connect these modifiers that are present in OpenCV, and you can sort of manipulate your image coming in from your camera to find your vision targets and isolate them from the rest of the image. And once you're happy with your resulting pipeline, your code flow, you can export it to this code file. It's called a code wrapper. You can place this code wrapper on your coprocessor's storage and route your images through it to isolate the actual vision target components from it. And this on its own is extremely powerful, and Grip is a great tool because you don't have to physically code the OpenCV pipeline. But it wouldn't be my first choice for anyone starting with Vision because it does require some knowledge of basic image processing, how OpenCV works, and how to actually implement it in code. So my choices for any first-time Vision programmers would definitely be a pre-made or a full-stack approach. And a pre-made implementation like Chameleon Vision, which is a program written by various developers from a variety of FRC teams, what it does is it runs its own server on any coprocessor that you like and allows users to tweak the computer vision algorithm through a GUI. So it's very user friendly. There's little maintenance that you have to do. All you have to do is just move some sliders to try and isolate your vision targets from your image. And the only difference between the pre-made and the full stack implementations that I've listed here is that the full stack implementation, like the Limelight, comes with its own coprocessor. So all you have to do is just wire it into your robot and you'll be up and running. Now, the downside to a component like the Limelight is that it is absurdly expensive, and you can get pretty much the same output from a Raspberry Pi with a webcam and Chameleon Vision, which is what we did this past year. Now, before we actually take a look at how we would find a target using Chameleon Vision or any other vision application, we need to understand how a computer is able to find any type of image within an image. So some of you may already be familiar with the RGB or red, green, blue color space, where we can represent a color as a mix of red, green, and blue values. So in this case, this green color right here is represented as a red value of 102, a green value of 255, and a B value of 51. So we can also represent this color as a mix of hue, saturation, and intensity values. And this is more beneficial to any computer vision application as we can more finely differentiate between parts of an image that might be similar colors but different shades or intensities. So it really allows us to fine tune those very similar parts of an image and really get the part of the image that we're looking for. So in this case, this image can be represented as a hue value of 105, a saturation value of 80, and an intensity value of 100. Since RGB really only communicates color info, if you were given these three RGB values, all you'd be able to say is that it's a green color that looks like this. Hue saturation values give us both color info and intensity info, so we can tell how bright or how dark this actual image is. Now, since we need to tell the computer to ignore the parts of the image that are not bright green, we utilize a technique known as HSV filtering. So HSV filtering is just a technique where you set a range of hue, saturation, and intensity values, and you only focus on the parts of the image that actually fall within those ranges. And through this technique, we can start to isolate our vision targets. Now let's take a look at the actual Chameleon Vision application. This is a web server running. This is identical to the web server that would be running on a coprocessor. Just for demonstration purposes, I have it running on my local machine, and I'm pretending that this is the image that the camera would be seeing. So as you can see, this image appears to be very dark anywhere that's not brightly lit up. And this is because what we've done to the image before it is being processed is we've lowered the exposure of the image. And exposure is just a value that tells you how much light is actually being let into the camera sensor. So the lower the exposure, the less light is being let into the sensor, which means the darker our overall image is going to be. By darkening our image, we're really giving a sharp contrast between the very bright parts of our image, such as the vision targets and, as you can see, some of the overhead lights here. So once we have this image in our Chameleon Vision GUI, we need to start actually filtering it. And we do that over here in this threshold tab. As you can see, we have three different sliders for our hue, our saturation, and our intensity values. And we can start to actually manipulate these sliders and tune the image to only show us these little vision tape right here. So as you can see, if I start moving this hue slider, these bounding boxes appear, but we can't actually tell what parts of the image are being isolated. So if we move over here into this threshold tab and we click this will highlight all the parts of the image that are passing through the filter. As you can see, it's all white because our filter is completely open. We haven't restricted anything. So typically when filtering images, you want to move top down. You want to start filtering your hue first, then your saturation, then your value, and this will, in most cases, get you a pretty decent filter that shouldn't change too much depending on light conditions. So I'm just gonna move these filters until I start to isolate the actual tape. And remember, what we're looking for is these two rectangles right here. So I'm gonna bring this bottom up and you can start to see the tape kind of come into frame. And now I've gone too far because most of the tape is black. It's not passing through the filter, so I'm going to back up on it a bit. And I'm gonna move from the opposite end to try and isolate anything that's not the same hue as the tape. So that does a pretty decent job. I don't want to go any further at risk of removing too much of the tape, so I'm going to move on to the saturation. Now that has the exact opposite effect of what we want because now we're isolating anything but the tape, so I'm going to leave that at 0 and go from the other end. And this does a much better job. Now you can see our tape is really isolated. And I'm going to go as far as I can without actually manipulating the tape too much. Back off a bit. Now I'm going to move on to the value slider. And this does a pretty decent job of getting rid of any of those small speckles that are remaining. And that was too far. So now, as you can see, we have a pretty decent filter that will, for the most part, track our image around. But as you can see, the program is getting confused by all of these small specks right here, which if you go back to the original image are the bright spots like the reflection off of the hatch panel and the overhead lights. So what we can do is we can use these two functions right here, which are OpenCV functions that help get rid of any unwanted noise. So for most cases, this erode function will get rid of most of your specs. And now, as you can see, uh, this this program will track our target almost no matter what. So finally, this contours tab is the last tab that you'll probably have to mess with, and most of the time you'll be changing this target group and this target intersection. So as you can see, if this was set to single, all it would do is it would pick up one of these targets, but if we set it to dual, it sees both of these two um, large areas and treats it as one target. And this target intersection has to do with the way the tape is angled. So as you can see, these two tapes are angled upwards. So we set the target intersection to upwards. If for any reason they were down, we would set to down. Since these are not downwards intersecting, they don't get picked up by the function. So I'm going to set that back to up and save it. And now that we've got our image completely filtered, we have to deal with um, actually making our robot target these targets. So that's where these values down here come to play, and for the most part, this yaw value is really the only value that you'll have to pay attention to. The yaw value essentially tells us how far away the target is from the very center of the camera. As you can see, the farther away it is, the more the yaw value increases. If I go the other direction, it's the same way, but just a different sign. So what we can do is we can actually uh, pass this yaw value back to our robot as part of a PID controller. So this value can be the sensor feedback for a PID controller, and we can set the set point to be 0 because, of course, if we were trying to line up on a target, we would want the yaw to be 0. So if you continually pass this yaw value back to a PID controller and have the robot turn, with a nicely tuned PID controller, you can have the robot turn and eventually center on the target. And that is what we did with the turret this past year. We had a motor that controlled the rotation of the turret. It got past the yaw value from the vision application, and based on that, it changed how fast and what direction it was rotating so that it would be centered on the actual vision target. And the great part about this application is that you can do virtually anything. There is a more complicated mode called the 3D mode or the PNP mode, which uses a pretty cool function of OpenCV that allows you to visualize your targets in 3D space. So if you just had a camera pointing at a target and you've done some small mathematical functions to actually model your camera behavior, what you can do is you can just point it at a vision target, upload a 3D model of the vision target, and this program will output where you are in 3D space relative to the target. And this can come very handy if you're doing any kind of shooting, because you can know just based off of this image how far back you are from the target, how far up the target is from your camera, and you can tune your flywheel shooting speeds based off of that. Um, Another important thing to note when you're doing vision processing is, since this is being calculated every single frame of video, it takes a lot of resources, and that exponentially increases the larger your video resolution is. So typically what people will do is they will set their resolution to something low, like 640 by 480, and you'll limit the FPS so that you can uh, consistently get a good output going to your vision application, so you can consistently run your vision algorithm almost every frame. Uh, Another great thing about this program is it has an additional mode for drivers. So with one button, you can just toggle back between vision mode and driver mode and use the same camera for both vision and driving purposes.